This is a slightly difficult question which involves a lot of concepts. You learn a lot from this question. The first thing, let me explain the question. What happens in the question is that from the initial position, the spring is cut at distance L by 3. Initially the spring is at its natural length. It is cut at distance L by 3 and then a mass m is inserted. After inserting that mass m, it comes down a little and it finally stabilizes at this final equilibrium position at a distance h from the ground. You need to find out this h and the total energy stored in the springs at this final position. So for this, the first thing, whenever springs are cut, always remember the spring constant of the remaining springs changes. It changes according to the rule. For a particular material of the spring, the spring constant into natural length is always equal to a constant. We write this as K into L equals C. So when we apply this on the given springs, initially K into L, we first find out the spring constant for spring S1. When the spring was cut, the lower spring was had a natural length of L by 3 equal to K dash into L by 3. So we get K dash is equal to 3K. So we know the spring constant for this spring as 3K. For S2, similarly we get K into L is equal to K double dash into 2L by 3. Therefore we get K double dash is equal to 3K by 2. So we now get the spring constants for both springs S1 and S2. We now want to find out what is this height h such that this comes to equilibrium. The mass of this is m. So when we consider this object, there is mgh acting in downward direction. Now this spring has been compressed. Therefore this spring will exert a force in the upward direction that is equal to the spring constant of the spring into the compression in the spring. The compression in the spring can be written as L by 3 was the natural length. Therefore L by 3 minus h is the compression in the spring. Therefore this is the force exerted by lower spring on the block in the upward direction. Now since the upper spring has been extended, it will exert again a force but in the upward direction. So this is a pushing force and this force by this spring is a pulling force because this spring has been compressed and this one has been extended. So the force by upper spring will be equal to the spring constant of the upper spring, that is 3K by 2, into the extension. The extension is again L by 3 minus h. We can write it directly also because the compression in the lower spring will be equal to the extension in the upper spring. So we can write it directly as L by 3 minus h. So for this mass m, we now balance these forces to get the equation mgh is equal to 3K plus 3K by 2 into L by 3 minus h. This comes out to be 8K by 9K by 2 into L by 3 minus h. From this we solve and get h is equal to L by 3 minus 2 mg upon 9K. So we get the answer for h. Now to find out the total energy stored in the springs, we simply have to write half the spring constant of one spring, that is half into 3K into x1 square plus half into 3k by 2 into x1 square again, because the extension and the compression in both the springs are same. So we can write this as x1 square by 2 into 9k by 2. Now x1 is equal to L by 3 minus h. So L by 3 minus h can be seen as 2 mg by 9k. So we can write x1 as 2 mg by 9k. Therefore the final answer becomes 2 mg by 9k whole square into 9k by 4. That is equal to m square g square upon 9k. So the final answer for the equilibrium height from the ground is L by 3 minus 2 mg upon 9k, and the total energy stored in the two springs at equilibrium is equal to m square g square upon 9k.